So the next part of the unit is projectile motion. A projectile is any object that's thrown into the air, such as a ball or a trapeze artist or a cannonball, or even packages that are dropped from flying objects. All of these objects have only one force that acts on them after the force that throws them. That force is the force of gravity. So the only force that's acting is gravity in minus 9.8 meters per second in the downwards direction, meters per second per second. Because of that, all projectiles follow a similar trajectory, and the trajectory follows a path called a parabola, which kind of looks like this. There are 3 or 4 different things that you can get from this type of graph, and one of them is the maximum height of the projectile, which is when the velocity is 0, which is basically when that derivative is 0. So when this point here is your maximum height. The other thing you can get is how long the projectile stays in the air, so the T max, you might call it. And that's until it falls to the ground and stop. The other thing you can look at is in the x direction, you might be looking at the maximum range of a projectile. All of these sorts of things are very important. So we're going to start with an example. This example is a helicopter that's delivering supplies to a farm. It's 100 meters above the ground, and it has to drop a package of supplies to fall to the ground. And you might be asked how long it takes for the package to reach the ground and how fast it's going when it hits the ground. These are things that you can do from the physics that you already know. So for example, if we use the initial equation, we can say, okay, initially it starts off at a height of 100 meters, and it starts off with a velocity in the y direction of 0. The only force that's acting on that's initial velocity, is 0 meters per second. The only force acting on that is gravity, of course, and we want to find out how long does it take to get to the ground. So what equations can we use? The simplest case is just to use the S equals ut plus a half at squared, which you'd use in the standard form. I'm going to actually write it in a different form so that it includes the vertical displacement that we already have, 100 meters, and also includes the y components of the velocity. So we're going to say S in the y direction is equal to sy0, so that's the initial displacement, plus we're going to say vy0, that's our initial velocity, times t, plus half a in the y direction, so that's the acceleration due to gravity just in the y direction, t squared. So that's our equation. I'm putting it in this form for a very good reason. We want to find out what happens when s is equal to 0. So we're going to make that 0. This is going to be 100 because that's our initial displacement. Our initial y velocity was 0, so that's just 0t. And here we're going to have half of the acceleration, which is minus 9.8 times t squared. So you can see this reduces down to a very simple equation of 100 times 2, it's going to be a negative, divided by negative 9.8. So the negatives cancel out, which is important because we're left with a square on the other side. So if we square root that, 200 over 9.8 square root, we get an answer for the solution, which is 4.52 seconds. So that's the time that it takes to drop the 100 meters. And what's the velocity when it finishes? Well, let's look at it. We're going to use the derivative of this equation. So we're going to have v of y is equal to vy0 plus a times t. So in this case, we want to find out what is that final velocity. Vy is equal to the initial velocity, which was 0. And it's just going to be the acceleration, which is minus 9.8 times t. And our t was 4.52. Which gives us an acceleration of minus 9.8 times 4.52, which is about 44.3 meters per second in the negative direction. So that's where we get our final velocity. If, of course, our helicopter, instead of being stationary, is actually moving, then you'll see that it follows this, an object that is dropped from the helicopter would follow a parabolic trajectory. So it would maintain its horizontal velocity, whatever horizontal velocity it had when it left the helicopter, but the vertical velocity would change due to acceleration. So, in the example here, again, this time the helicopter is travelling at 20 metres per second, 100 metres above the ground. How long does it take for the package to hit the ground? Well, it's exactly the same amount of time. So you can use this same equation and you'll get the same answer. The time is 4.52 seconds. The horizontal component, however, has to be used here. So if we use the horizontal component of velocity, what we're using is a simplified example of our horizontal displacement. So we can use Sx is equal to Vx0 times t plus a half a in the x direction times t squared. But remember that there is no acceleration in the x direction, so that's 0. So our simple equation is just that displacement is equal to the initial velocity times the time. So that's our 4.52 times 20 metres per second. It gives you 90 metres. The velocity when the package hits the ground in the vertical direction will still be the same, so it'll still be 44.3 metres per second. However, you're still going to have that horizontal component of velocity. So what happens is when it hits the ground, it's hitting at an angle, and that means that it's going to have a vertical component of velocity, which was 44.3 metres per second, and it's also going to have a horizontal component of velocity, which was 20 metres per second. So we could use Pythagoras in this case just to find out what the actual velocity was. Let's see, V0 or V final squared is going to be equal to 20 squared plus 44.3 squared. V final is the square root of 20 squared plus 44.3 squared, which is 48.6 metres per second. Remembering, of course, that that is in the negative direction anyway.